Students, I am Salil Srivastava. I have done my B.Tech from I.I.T Kanpur and M.Tech from I.I.T Roorkee. I have been teaching maths and physics to I.I.T JEE aspirants for last 24 years since 1996. As you know that human race is passing through a bad phase, but the show must go on. Only way I can afford to interact with my students is through online lectures. I've already posted the first lecture 2 days back. If you haven't watched that, the link is in the description. Now we are creating the second video on the electrostatics.
Well, this is Erodo 3.3. This is Erodo 3.3, and I've already discussed a question in the previous lecture. This is the next question, second question that I'm discussing after the Coulomb law on the application of Coulomb law. So this is two small equally charged spheres, each of mass m, are suspended from the same point by silk thread of length L. The distance between the sphere, which is x, is much bigger than L. Find the rate dq by dt with which the charge leaks off each sphere if the approach velocity varies as v is equal to a upon root x, where a is constant. Again, it is quite similar to the previous one which I have taken in the previous lecture. Now here in this case I need to draw the free body diagram again. So this is how it is suspended. So this is the ceiling from where it is suspended. Let me make the ceiling like this, and this can be the vertical passing through the ceiling. For the sake of correctness, I am drawing right, and these are the strings, two strings. These are the two strings on which the charges. These are the two strings on which the charges are attached and hung from the ceiling. So maybe this is the charge here, this is the charge here, and they're hung from the ceiling. As it was mentioned in the question that the distance between them is x. So this is x for you, right? Okay, x. Both the charges are q and q each. The length of the string is L each. Let us say that this angle is theta. So now if I draw the free body diagram of the charges, any one can be drawn. Both are identically placed. So they look like interaction with the earth, mg, right, and Coulombic repulsion, and the tension in the string. This is mg, this is the Coulombic repulsion F. For the time being I am calling it. I'll write the expression for it later when I manipulate them in the algebraic expressions. So if I draw the vertical through this, then alternate angles are equal. That's why this angle will also be theta. You can write the chart somewhere else so that it is not filthy. Maybe somewhere over here, right? Now you can see that if I apply the force balance for this charge, then I get to see that T cos theta is equal to mg and T sine theta is equal to F, which is Q square upon 4 pi epsilon naught and x square. Now if I take the ratio, second equation upon the first equation, I get tan theta is equal to Q square upon 4 pi epsilon naught x square mg. But you know that for a small angle, in radian, sin theta is nearly equal to tan theta is nearly equal to theta. Thus, we can afford to write it as E is equal to sin theta also, rather nearly equal to sin theta. But sin theta can be comfortably written in this triangle. So I get to see that Q square upon 4 pi epsilon naught x square mg is gonna be equal to sin theta is x by 2 upon L, and thus I can comfortably get the expression for charge in terms of the distance between the charges, that is x. So Q square comes out to be, of course, I cross multiply over here and I get 2 pi epsilon naught and x cube mg right upon L, from where I get Q is 2 pi epsilon naught mg upon L raised power 1 by 2 and x raised power 3 by 2. I have deliberately kept everything which is constant inside the bracket and variable outside. Now if I differentiate both sides with respect to t, I get dq by dt is equal to, this being constant is copied, mg upon L raised to the power 1 by 2. I apply chain rule over here. I can write it as d by dx of x raised power 3 by 2 into dx by dt. So needless to say that I get to see this as 2 pi epsilon naught mg upon L raised to the power 1 by 2 into 3 by 2 x raised power 1 by 2, that is root x, and dx by dt is the velocity. And what is the velocity that they have given? In the question, they have given the velocity as a by root x, where a is a constant. So needless to say that we can plug it back over here and can write it as a by root x. That's beautiful. Root x gets cancelled out, and you get to see that the rate of leakage of charge which they are asking is nothing but 3 by 2 a 2 pi epsilon naught mg upon L raised to the power 1 by 2, and that is the answer to this question. Well, this is the next question, A particle A having a charge Q, which is equal to 5 into 10 power minus 7 coulomb, is fixed in a vertical wall. The second particle B of mass 100 gram and having equal charge is suspended by a silk thread of length 30 centimeter from the wall. The point of suspension is 30 centimeter above the particle A. Find the angle of the thread with the vertical when it stays in equilibrium. So again, this would be based upon force balance. If I can afford to draw the free body diagram, well, this may be the vertical wall which we are talking about, and right. So out here, there's a charge that is fixed somewhere over here. Let me make the charge somewhere over here, right? This is the charge A, okay. This is the charge A, and another charge is suspended by a string, insulating string, which is this, and we have this charge which is identical to the previous one. You can write it over here, right? And this is B. This is the point of suspension. Let's call this point of suspension as O, right? Now, OA as well as OB is given to be 30 centimeter. OA is equal to OB is equal to 30 centimeter. So if I join this, this will make isosceles triangle, If I join this, so this is what would be isosceles triangle. If I draw the free body diagram of this particle B, particle A anyway is fixed on the wall. If I draw the free body diagram, it looks like interaction with the earth, mg, Coulombic repulsion, F. So let me write the name of the forces, mgf, and of course the third force is tension in the string. You can show something like this, T. Now, if I see the angle that these three forces are making with each other, finally we require to find this angle the string is making with the vertical. Let's call this theta. So you can see that this is the isosceles triangle. If I join this point of suspension with the midpoint of line joining the two, this will be perpendicular, and thus you can see that this being a right angle triangle, this angle would be this angle would be theta by 2. That's why this angle would be 90 minus theta by 2. I can show it. This is a small figure. Let me write somewhere over here that it is pi by 2 minus theta by 2. Right? Now, as far as angle between tension T and force F is concerned, we can use the theorem we learned in the geometry. That is, external angle is the sum of the internal two. Let me show that. This being the external angle would be sum of this angle and this angle. So thus, what we can afford to do is, if this angle is alpha for the time being, let's say, so alpha is gonna be equal to what? External angle, that is theta plus pi by 2 minus theta by 2, which is gonna be pi by 2 plus theta by 2. And this angle, which I can show with different color, this angle is nothing but this angle is gonna be pi minus theta. Why? Because mg and wall both are vertical, they are parallel. So this string can be considered as a transversal, and you know that when two parallel lines are cut by a transversal, the sum of the internal angle is pi. So let's get rid of this. So this angle is pi minus theta. Now, having known these two angles, that is alpha and this angle is pi minus theta, I can apply what is known as Lamy's theorem to relate the force and the tension, which will finally render the expression for theta. How? If I draw it separately, then this is my force F, this is my force F, this is the tension T, and this is mg, and you know what? This is mg, this is F, Coulombic repulsion, this is tension, and this angle is, which is alpha, is nothing but pi by 2 plus theta by 2, pi by 2 plus theta by 2, and this angle is pi minus theta. If I apply Lamy's theorem, what is Lamy's theorem? Lamy's theorem says that if three forces are in equilibrium, then every force is proportional to sine of angle between the other two forces. So, what it will mean is F upon sine pi minus theta is equal to mg upon sine pi by 2 plus theta by 2. Now, which can be written as F upon sine theta is equal to mg upon cos theta by 2. Now it is the time to put the value of force F. Force F is the Coulombic repulsion between these two charges, and you can see that the distance between them, that is AB, is gonna be nothing but, if I can write it over here, AB is gonna be nothing but, I can find it by finding the half of the distance between AB and then doubling this. Since let's call this as L, OA and OB. So this is my L and this is also L. So half of the distance between A and B would be L sine theta by 2. So AB would be 2L sine theta by 2. So this is the distance between the two charges, which I'll use for writing the expression of force in the Coulomb law. So force F would be Q square upon 4 pi epsilon naught, and distance square, that is 2L sine theta by 2, the 2L sine theta by 2 square, right? And of course, one more sine theta, which was already there in this statement, is equal to mg upon cos theta by 2. Well, this sine theta can be broken down into half angle, that is 2 sine theta by 2 cos theta by 2. So 1 cos theta by 2 will get cancelled off, and I get to see finally q square upon 16 pi epsilon naught L square into sine square theta by 2 into 2 sine theta by 2 into cos theta by 2. I have broken into half angle, is gonna be equal to mg upon cos theta by 2. Cos theta by 2 gets cancelled off both sides, and I finally get sine cube theta by 2 is equal to Q square upon a long expression. What is that? That is 32 pi epsilon naught mg L square. I cube root it and I get the answer. That is why my sine theta by 2 would be equal to Q square upon 32 pi epsilon naught mg L square raised to the power 1 by 3, and thus finally my theta is going to be 2 sine inverse, and of course Q square upon 32 pi epsilon naught mg L square raised to the power 1 by 3. I can place the curly bracket to ensure that we are taking the sine inverse of this quantity, and that is the answer. Well, this is the next question for my online student. My humble request to you all is, please stay indoor. Please follow all the regulations imposed by the law enforcing authorities, and you are serving the humanity by isolating yourself and not violating any norms which are imposed by the government. Okay, let's come back to the question. Two equal positive point charges are separated by a distance 2a. Point test charge is located in a plane which is normal to the line joining these charges and midway between them. Calculate the radius r of the circle of symmetry in this plane for which the force on the test charge has a maximum value. Well, it is a question where we have to conceive it in three-dimensional space. So these are the two charges which are, let me just scroll down if you can afford to write down the question. Then I need larger space for this. So these are the two charges which are separated by certain distance between them. Maybe charges are this and this, equal charges, identical. Let's call both of them as Q. So there is a plane of symmetry. Although I'm drawing it in line, but think that it is a plane, It is a plane which is perpendicular bisector of the line joining the two charges. Now what they're asking is, you have to find the radius of the circle, maybe this, okay. So let me do away with this and draw it correctly. So this was the plane of symmetry. This was the plane of symmetry, And this is a circle on this. They're asking the radius of the circle, this blue dotted circle, so that the force on the charge kept at this point is maximum. Well, if you read the question, then there's a charge that is kept at this point. So let's call this charge as Q naught. This charge is Q naught. It can be kept anywhere. It can be kept here, it can be kept here, it can be kept here, or here, or here, anywhere. After all, it is a circle. So, if I see the force that is felt by Q naught, which I write somewhere over here for the sake of convenience, Q naught, maybe I write it here over here or somewhere over here would be better, I guess. Q naught. So if I see the force on this charge, it will be acting along this line. Of course, due to this, it will be acting along this line. The forces are, you can see, I'm showing with another color, this and this, They both would be equal in magnitude after all. Let's call them both as F, The total distance between the two charges 2a. That's why distance from here to here as well as distance from here to here would be a. This both are a after all. If the radius of the circle is r, you can see that the distance, which is the hypotenuse of this right angle triangle, would be under root a square plus r square. If I call this angle as theta, of course, which is going to be same as this angle as well. So the total force that would be acting on the charge would be the resultant of these two orange forces. If I show the total force, effective force that is acting on the charge Q naught as F dash, then what would be F dash? F dash would be 2F cos theta, because once I break them down into components, I'm showing, I'll undo that step. If I break them down into components, then their transverse component would cancel off. That is, this and this would cancel off, and the longitudinal component will reinforce each other. That's why we have the 2f cos theta. Let me undo this step. Okay. And what is this F after all? It is the Coulombic force, so which is gonna be, I can compute for any charge, either left charge or right charge, and it is gonna be equal to Q naught upon 4 pi epsilon naught, and the distance square, that is a square plus r square, multiplied by cos theta, and the cos theta in this alternate angles are equal. That's why this angle is also theta after all. And thus you can see that the cos theta is based upon hypotenuse, which is nothing but r upon under root a square plus r square. The expression for the total force on the charge becomes Q naught upon 2 pi epsilon naught. Rather, I write it over here in the center of it, 2 pi epsilon naught, and the variable part is r upon a square plus r square raised to the power 3 by 2. Well, this I need to find the maximum value of f. One way of doing it is rather mechanical, that is, you differentiate with respect to r and equate it to 0 to get the optimum value. That anybody will do. I'll tell you something else. I can use arithmetic mean and geometric mean inequality to find the maximum value of this. How? After all, I have to find the maximum value of, r upon a square plus r square raised to the power 3 by 2 because remaining part is constant. So I have to maximize this. So we can afford to do that. I have to write again a square plus r square raised to the power 3 by 2. See, the same thing can be written as r upon a square plus r square raised to the power 3 by 2 can be written as 1 upon a square plus r square raised to the power 3 by 2 upon r. R goes inside and it becomes 1 upon a square plus r square raised to the power r raised to the power 2 by 3. This is the important step. Remember that when this power, then this denominator will be taken out, so these two power will get multiplied to become 1, which is here as well. Now the same expression becomes equal to what? The same expression becomes equal to 1 upon a square by r raised to power 2 by 3 plus r raised to power 4 by 3 raised to the power 3 by 2, of course, outside. Very judiciously, what we do is we write it as 1 upon a square by 2 2r raised to the power 2 by 3 plus a square upon 2r raised to the power 2 by 3 plus r raised to the power 4 by 3 raised to the power 3 by 2. You can see that I have done nothing but I have broken it down into two parts, both half of this. So this has been broken down into these two. Divide by 2, any number can be written as twice the sum of half of the number. So this is what I have done. Why I have done this? I have done this to apply AM and GM inequality. Look at the denominator. If we apply AM is greater than or equal to GM for numbers, for expressions rather, a square by 2 r raised to the power 2 by 3 comma a square upon 2 r raised to the power 2 by 3 comma r raised to the power 4 by 3. What do we get? AM is greater than or equal to GM. That is why we have a raised to the power a square upon 2 raised to the power 2 by 3 plus a square upon 2r raised to the power 2 by 3 plus r raised to the power 4 by 3 upon 3. After all, we are taking the arithmetic mean of three numbers. Is greater than or equal to the geometric mean, product of them all. So that is a square by 2r raised to the power 2 by 3 into a square by 2r raised to the power 2 by 3. Let me write it neatly. Here 2r raised to the power 2 by 3 into r raised to the power 4 by 3 raised to the power 1 by 3 because we are taking the geometric mean of three numbers, which renders, you can see over here, which renders a square by r raised to the power 2 by 3 plus r raised to the power 4 by 3 is greater than or equal to 3 times of this. 3 goes over here and a raised to the power 4 upon 4 raised to the power 1 by 3, which is the constant. That means it is the minimum value of this. That means minimum value of a square upon r raised power 2 by 3 plus r raised power 4 by 3 is 3 upon 4 raised power 1 by 3 into a raised power 4 by 3. When will this achieve this minimum value? When all the numbers on which arithmetic mean and geometric mean is applied are equal. These two are already equal. That's why we only need to make these two equal. And thus, this happens for what? For r raised power 4 by 3 is equal to a square upon r 2r raised to the power 2 by 3. Cross multiply, I get r square is equal to a square by 2, which implies r is equal to a upon root 2, which is the answer. So, the radius of the circle on the bisector plane at which the charge q naught must be kept should be a upon root 2 to feel the maximum force. That is the answer. Since this is occurring in the denominator of the total force, that is why when its value would be minimum, the force would be maximum. Well, this could have been done in rather lesser number of steps by simply being mechanical and differentiating the expression for my force F. But I just wanted to give you another way of dealing with the same issue. I could have differentiated this and got the answer in lesser number of steps. But I just wanted to give another perspective because sometimes this may work very beautifully. I still recall that in JEE 2000 screening, there was a question based upon which was on the topic electromagnetic induction, which you'll learn decently later. That was again inquiring the maximum minimum value of some physical quantity, which was very complicated by differentiating, and it was done in just 2 lines by applying AMGM. So I just wanted to give you another perspective of this. I know that this could have been much more simply handled by differentiating, but that is what it is. So this should be the radius. Well, this is the next question. It was asked in I.I.T JEE Advanced 2014. As you can see, this is the match the following kind of question. Out here there are 4 charges which are placed on x-axis. You can call, for the sake of calling, the x-axis as this, positive x-axis, and positive y-axis as this, and there's the charge q that is placed over here. So rather I'll prefer to draw it with the dotted line so that it does not overwrite the given informations. So this is x-axis, this is y-axis, positive x and y-axis. So this is what it is, x-axis and okay, maybe x-axis and y-axis. Now they're asking that there are 4 charges q1, q2, q3, q4. They're all equal. You can see here they're all same magnitude. Not equal, equal would be the wrong word because they may be different in sign. Same magnitude. Now they're saying that if you have to match the list 1 with list 2. First, if all the 4 charges are positive, you can see that what is going to happen over here. Well, if I can show, I'll undo that later on. The force due to Q1 would be somewhere over here, repulsive force, because Q is positive as it is given, right? A positive charge. So you can see that this is a positive charge Q. So this would be repulsive due to this because this is positive, and this again would be repulsive. This again would be repulsive, and being nearer, it would be larger as compared to Q1 and Q4, and this also would be repulsive. If you can see that sum of all these four forces definitely due to symmetry is gonna come out to be along, I can confirm that it is gonna come out to be along this. That is why in the positive x direction. So that shows that for P, the option would be 3. So I can undo that. If we have understood this, I can undo that because I have to go to the second part of it as well. I do all the thing that I have drawn. I undo maybe the information that is important for that part. I can still keep it. I can see that P is matching with 3, already explained, right? P is matching with 3. If I go to the Q part, Q1, Q2 positive, Q3, Q4 negative. So Q1 and Q2 are positive. So this is positive, this is positive. No, this is positive, and these two are negative. If these two are negative, then needless to say that the forces would be, again I draw, because of these two would be the repulsive force, maybe something like this, and because of these two would be the attractive force, Q3, and because of Q4, and you can see at once that is these forces would be oriented like this. If I can show their direction, they are finally heading towards this, these four forces will definitely find their resultant ultimately in this direction, which is what? Which is positive x direction. Positive x direction, that means the first option. So Q is matching with first. You have understood this probably because it is the online interaction. So you can pause the video for a while to understand this, and I can undo the drawings so that I can go to the third part. So I'm undoing. So this is matching with the first. Now come to the third one. Q1, Q4 are positive. This is positive, and Q2, Q3 are negative. These two are negative. So because of these two would be the repulsive force. This would be repulsive, this would be repulsive, like charges repel, unlike charges attract, and because of these two would be attractive force. Because of these two would be attractive force. But you can see that so these two will sum up to their own value. These two will sum up to their own value, they being smaller forces. Why? Because the distance of Q1 and Q4 are larger. They are a larger distance as compared to Q2 and Q3. That's why these two forces are weaker as compared to this. That's why the resultant of the upper two forces would be subdued to resultant of the lower two forces. These two forces. That's the overall difference will come out to be, I'm making thicker and showing it here, and these two will come out to be in this direction. Maybe quite thick it was, so let me just, maybe I can use different color as well. The resultant of these two would be overall in this direction. Agree? That means in the negative y direction because of the dominance of the force in the downward direction. Okay, so negative y means 4. So R would be matching with 4, right? Again, you can pause the screen for a while and to go through all the steps which I have discussed, and I'm undoing all the drawing to take the fourth part. The conclusion was that R is matching with 4. R is matching with 4, and now really we don't need to check the fourth S part because only the A option has these three options, that is P3, Q1, RS, R4. So even then, for the sake of completeness, let me discuss the fourth part as well. Here Q1 and Q3 are positive. So here, okay, here Q1 and Q3 are positive. Q1 and Q3. Q1 and Q3 are positive. Now you can see that in the fourth option, Q1 and Q3 are positive. So this is positive and this is positive, and Q2 and Q4 are negative. So force due to these charges would be Q1 is positive, that's why we have the repulsive force, So maybe I can show with the dotted line, and finally something like this, Okay, this is what it is. And due to Q2 is this way, so let me draw only the line, not the arrow. So it would be along this line, it would be along this line, It would be along this line, it would be along this line. Let me draw the line first. Okay, now the forces. So this is repulsive due to Q1, that's why it would be this. And due to Q2, it is attractive, but is nearer, that's why much larger force. And Q3 is positive, that's why repulsive, it is nearer, that's why again a large force which is equal to this in magnitude. Q4, they'll be attractive, but it will be as large in magnitude as due to Q1 because they are symmetrically placed, that's why it would be attractive like this. So these two will have their resultant, these two forces that in the leftward direction will have their resultant in the leftward direction, whereas these two forces would have their resultant in the rightward direction. You can see that because leftward forces are larger, that's why this will dominate. Leftward force will dominate the rightward force. And hence, as I said earlier also in the second part maybe, that is this, the resultant of these two black forces dominate in the leftward direction. Right? So that should be minus x. So I think for S, the answer should be 2. So this is how it is, So again, you freeze the screen and then understand the step which I have discussed. I'm undoing the steps for clearer view. So, or maybe we can retain it because this is the last part, so it does not make any difference at all. So, well, this would be we have R4 which was undone unknowingly and S2. The final answer is, of course, A. Nice question it was. That completes the discussion for this question. Well, this is the final question for today's lecture. And this is 3.5 Erodo. This notion that we are learning here is applicable in many topics. And this is one of the application. One more question we'll get to see in magnetic forces also. 3.152, I believe that would be 3.252. Anyways, we'll take it up later. For the time being, it is on Coulomb's law, and the general notion is known as hoop stress. It is known as hoop, which is ring. So it is known as hoop stress. So what they have said is a thin wire ring of radius r has an electric charge. A thin wire ring of radius r has an electric charge q. What will be the increment in the force stretching the wire if the point charge q naught is placed at the ring center? So if I keep a charge maybe somewhere over here, which is the central charge, and what they're saying is there's a ring, which is again charged. So this can be the ring. Okay. This ring has a distributed charge Q. This ring has a distributed charge Q, and this is Q naught. Well, if I take a very small part of this ring, very small part, which I call elemental or infinitesimal, also it is known as, I'm just drawing the vertical, there's nothing to do with this. If you consider this a bangle, so I take a small broken part of the bangle, a small circular element. So maybe I'm taking this element only, that is from here to here, which is subtending angle theta, very small angle theta. Agree? So I separate this part and draw it in a separate diagram. So I draw this part separately. This is drawn thinner, but don't mind that. This is this part of the broken bangle. So if I reconstruct all the lines over here, this is the line vertical, and this is the line joining these blue lines. I already called this angle as theta, so this angle would be, of course, theta by 2. This angle would be again theta by 2. If I draw the free body diagram of this element, which I have broken down, then there will be three forces acting. And there would be Coulombic repulsion. Sorry, let me place the charge first. And then this may be Q naught, somewhere over here. And how much is this charge? Let's call this charge as dq. Let's call this charge as dq. So I call this charge as dq. How much would be the charge dq? Or rather q, you can call it q itself or dq. It does not make any difference at all. It is a very small charge. From unitary law, since in 2 pi radians the charge q is spread, hence in unit radian q by 2 pi charge would be placed, and hence in theta radians the charge would be q by 2 pi into theta. And thus the force which are acting on this element is Coulombic repulsion, tension T, and we are required to find this tension T. This force can be called as F, Coulombic repulsion. This is tension T, this is tension T. Now if I draw a horizontal line over here, maybe somewhere over here. Yes, for the sake of drawing it. You know that angle between two lines is equal to angle between their perpendiculars. This blue line is perpendicular to this green line. This dotted white line is perpendicular to this white line. That's why this angle will also be d theta by 2. And likewise, this angle will also be d theta by 2. So if I break these three forces in horizontal and vertical component, so you can see that the horizontal component of T, which I can show it here as this and this, this and this, maybe some different color, this and this, and this and this. The horizontal component will cancel off. Will they cancel off or not? Leaving the downward component, which collectively will balance the force F. You may pause the video for a while here and understand what I have said in the last 30 seconds probably. I said these two transverse component will cancel off and the downward component will collectively balance the Coulombic repulsion F. Thus, let me undo the unwanted drawings. So thus, you can see that T, sorry, I called it theta, not d theta. I called it theta by 2. Theta by 2. Okay, so you can see that the downward component would be t sine theta by 2, t sine theta by 2. So thus 2t sine theta by 2 would be f, which is what? Q naught into q theta by 2 pi. Let me write neatly. Maybe I can shift q naught slightly upwards to create a space for it. Q theta by 2 pi upon, okay, upon 4 pi epsilon naught r square, where r is the radius of the ring, Small r they have written in the book. Let me also write small r. You can see that in the LHS for small angle sine theta, I already used this concept today. For a small angle, sine theta is nearly equal to theta. Maybe I can write neatly. For a small angle, sine theta is nearly equal to theta. Thus, out here, this will become 2t into theta by 2 would be nothing but q naught q right theta upon 8 pi square epsilon naught r square, implying that when I cancel it off, I get to see right. Maybe I can shift the figure slightly upwards, Why? Because I need to create a space for this. Somewhere over here. Okay, let me cancel it over here. And thus I get to see, can I afford to write the answer here? Can I afford to write the answer over here? So this 2 and 2 gets cancelled off. This 2 and 2 gets cancelled off. Theta gets cancelled off. And I get the hoop stress. I get the hoop stress which they are asking in a different world. That is T equal to Q naught Q upon 8 pi square epsilon naught r square as the final answer. Right? So this completes the discussion for today's lecture. Happy learning. Stay home. Stay hygienic. Wash your hands regularly. We together have to defeat this common enemy of humanity. We'll see you in the next lecture.